Hello, everybody. Welcome to today's current seminar. Today we have two speakers. Our first speaker is Zheyuan Hu. He will be giving a talk on tackling the curse of dimensionality with physics-informed neural networks. Zheyuan Hu is a PhD student in computer science at the National University of Singapore, advised by Professor Kanji Kawaguchi. His research interests are AI for science, scientific machine learning, and physics-informed neural networks. Recently, he has done a series of research to tackle the curse of dimensionality and solve high-dimensional, high-order PDEs with PINs. With that short introduction, the floor is yours, and you can start your presentation.
Yeah, thanks for the introduction. So, hi everyone. So, I'm Zheyuan Hu, and I'm going to talk about tackling the curse of dimensionality with pins. So, I'm going to cover two papers in this talk. The first is our initial paper, tackling the curse of dimensionality with pins, and another paper on Hutchinson trace estimation for high-dimensional and high-order pins. And I would like to thank all the collaborators, Dr. Shukla, my supervisor, Kenji Kawaguchi, and my lab mate, Sekun Shi, and also Professor Kanadakis for their support. And let's go to the introduction. So for the problem definition, the curse of dimensionality refers to the exponentially increasing computational and memory challenges when dealing with high-dimensional PDEs problems. It was introduced in 1957 by Richard E. Bellman when he was researching on dynamic programming. So COD poses a great challenge to solving high-dimensional PDEs, to classical finite difference method and finite element method, because they are based on a grid, and the grid size can grow exponentially. So before our paper, actually pins are somehow very promising in solving the COD problem, because it can enable mesh-free training and use neural networks as the surrogate model. So it is mesh-free. We can sample points using Monte Carlo, so it will not suffer from COD. And neural networks are proven to be efficient in high-dimensional fitting, like in imaging science and also language processing. So neural network is a very attractive choice for high-dimensional PDEs and learning the high-dimensional functions. However, PIN may fail due to the huge automatic differentiation cost in high-dimensional settings. So if we come to many dimensions, like thousands of dimensions and even millions of dimensions, then PIN will fail. So overall, PIN encounters the phenomenon of insufficient memory and slow convergence due to the huge amount of differentiations in the PDE. So when the dimension of the PDE is high enough, even if you use one collocation residual point, you will get an insufficient memory error. This is due to the many automatic differentiation corresponding to different dimensions. So to this end, we first proposed a training method of pins by decomposing and sampling gradients of PDEs, which we named stochastic dimension gradient descent, SDGD. So it accelerates the training of pin while significantly reducing the memory cost. So the core idea is to decompose the gradient or the residual of a pin into pieces corresponding to different dimensions, and we sample randomly a subset of these dimension pieces in each iteration of training. So let's go to some technical details after the introduction. So first, we briefly review pins. So we consider a general PDE problem defined on the domain. So we have a residual part and a boundary condition. So we use a PIN, which is a neural network-based PDE solver. We are minimizing the boundary loss LB zeta and residual loss LR zeta, and zeta is the model parameter. So we sample residual points and boundary points to minimize the loss, to minimize the discrepancy between the neural network and the residual also on the boundary. So you can see that the key computational bottleneck will be the residual loss, because on boundary, we usually have lower order derivatives, but in residual condition, which is the LUX, we have higher order or the highest order derivative in the PDE. So the residual part is the most costly, both in high dimension and low dimension setting. So let's go to the technical details of SDG. So for illustration, I will use a relatively simple high-dimensional second-order Poisson equation for illustration, and I think it is the most classical one to demonstrate the idea. So we consider Poisson equation, which is second-order and high dimension. So here I give the expression in equation 3. So here D is the dimension of the problem. So we have D second order derivatives along different input dimensions. And here U is the solution, and we'll use U theta, which is the pin model, to fit the residual. So the key is that you can see that if we use the PD in equation 3, then the memory and the computational cost scale fast as the dimension D increases. So the second order derivatives are the main computational burden. So if the dimension is high enough, then if you only use one residual point, it can lead to insufficient memory error. And the cost cannot be further reduced since your batch size for residual point is already 1. So you cannot decompose it further. And then we can say that, okay, pin directly failed due to the vast amount of second order derivatives. So to this end, we propose SDGD to further decompose the residual for speed up and scale up. So the key of SDG is that the key observation is that we can rewrite the Laplacian operator in the Poisson equation as an expectation as a sum between different dimensions. So here we can rewrite the Poisson equation as D times an expectation over the dimension index. So since we can write it, so here index I is uniformly sampled from all dimensions 1 to until D. So we can sample dimension index I to form an unbiased residual estimation, which can be minimized efficiently. So the key idea is that we randomly sample an index set I, which is a subset of all dimensions. So after we sample it, then we can estimate the residual randomly and cheaply using the expression in equation 5. So the key is the red part. So you can see that instead of estimating the residual from all dimensions, we only estimate the residual via part of the dimension. So if we estimate it from part of the dimension, then we can control the batch size. We can control the size of index set I to make the residual estimation much cheaper. And then we know that the estimation 5 is in expectation, it is the exact residual once we take expectation of the index set I. So we can plug this estimation into the residual loss. As I mentioned, the residual loss will be considered as the main computational burden bottleneck. So instead of optimizing the expensive full residual loss in equation 6, so here I drop. So I only consider the residual loss over 1 point x. So you can also consider residual loss for multiple point x, but this is the same. So I just want to simplify the notation. We are considering only one residual point. So in equation 6, it is the full residual loss. We minimize the residual using the all d dimension second order derivative. So we can plug the estimated random residual into the residual loss with an index set I. So in equation 7, we plug our previous residual random estimator into the loss function. So we are minimizing the loss in equation 7. We are in expectation of minimizing the full residual loss. One thing to note that the loss in equation 7 is an biased estimator, because although the sampled SDGD residual is an unbiased estimator of the full residual, the loss function is a mean square error loss function. So the mean square error is square, so it's non-linear. So we do not have the linearity of the expectation. So equation 7 is biased. So to de-bias the loss function, we can sample the index set twice with two independent index sets, I and j, to de-bias that. So the last loss function in equation 8 is an unbiased estimator. So you can see that we have two index sets. So the expectation of equation 8 over I and j will be 6, which is the full residual loss. So by doing that, we can obtain a very cheap estimation of the residual loss. So we avoid computing the full gradient, and then we are somehow decomposing the residual loss more. So it's called that's why it's called SDGD. It's somehow similar to stochastic gradient descent. Just the stochasticity is over the dimension. Okay, so here are the technical details. So we do a simple summary for the idea of the SDGD. So first, we can speed up and scale up pins. So the scale up is from we are only backpropagating over part of the dimension, not all. So the memory cost is reduced. Another thing is that we are using some stochastic gradient. And as you know, stochastic gradient is the key component to modern machine learning. So we in modern machine learning and also low dimensional pin, we usually sample a proper number of residual point or proper number of data for backpropagation, not all, because estimating the loss on all data will be very expensive. So the idea is the same. We do not backpropagate all the dimension in SDGD. We just choose a few dimensions for backpropagation. So it also is random, and it's random. It can unbiasedly estimate the exact residual. So in expectation, we are still converging to the optimal point. So also, since we show that SDGD is unbiased estimator, it can be combined with modern optimizers like Adam. So you just need to minimize equation 7 and equation 8. So they are all loss functions. So no matter which optimator, you can choose any optimizer you want. So another key philosophy, as I mentioned, is that we usually sample a proper number of residual points in low dimensional pin rather than a lot. This is to reduce the cost of each gradient while keeping the gradient unbiased. So when it comes to high dimensions, why don't we sample dimensions just like we sample point? So this is the introduction to SDGD, and this is only the first paper. So in the following, I would like to introduce another high-dimensional pin accelerator, Hutchinson trace estimation, and in abbreviation HTE, and it can also do something similar to SDGD, but from the perspective of Hessian matrix trace perspective. So, but later I will actually unify SDGD with Hutchinson trace estimation and compare their difference and similarity. So the Hutchinson trace estimation views the Laplacian operator in the Poisson equation as the trace of the Hessian matrix. So the key observation is equation 9. It's relatively trivial, which is the Laplacian is the Hessian trace. So we can recall some classical mathematics like the trace of a matrix A can be estimated randomly. So the trace A equals which is an expectation of a Hessian vector product V transpose A times V. So for all random variables V, which is a d-dimensional vector, such that the covariance matrix V times V transpose, the expectation will be the identity. So this is relatively easy to prove using some linear algebra. Then we can estimate the trace, especially the Hessian trace, by Monte Carlo. So we replace estimating the Hessian trace by some Hessian vector product. This is something like SDGD. So we are all also obtaining some random estimator of the full Laplacian, which is the Hessian trace. So we can also, by using this idea, we can apply the Hutchinson trace estimation to a border class of second-order parabolic equations. It has numerous applications, and it is actually the hottest area in high-dimensional PDEs. Also, SDGD can be applied, so I will introduce it later. We also show that SDGD and HTE can be applied to other kind of equations, but I would like to focus on these kind of second-order equations because they are the hottest topic and has the most vast applications. So it can cover Fokker-Planck equation from statistical mechanics to describe the evolution of stochastic differential equations, SDEs, and recently, the Fokker-Planck equation can be used for image generation in some diffusion model like stable diffusion, mid-journey, and their underlying mechanics will be the Fokker-Planck equation. So the Fokker-Planck equation in nowadays is very practical in image generation, but it is another topic. So I just want to let you know that PDEs are very practical today and with numerous applications. And the second example is the Black-Scholes equation in mathematical finance. So in option pricing, we usually have many options or many stocks. So if we want to compute their evolution, then it will be a high-dimensional PDE. And it is also one kind of second-order parabolic equations. And the third example is Hamilton-Jacobi-Bellman equation in optimal control. And it is also some famous PDE because the curse of dimensionality, which is the core of this talk, comes from optimal control when the mathematician Richard E. Bellman was researching optimal control. So the fourth example will be Schrodinger equation. It is also second order equation, but it can be also time independent. So, but it is second order and it is in quantum physics. So as you know, solving the Schrodinger equation, if we can solve Schrodinger equation efficiently, then we can compute the properties of some molecules efficiently, which can be used for some material design and also like drug design. So it's very broad application. So we will focus on these kind of second order parabolic equations with this form. So you can see that the key is still the Hessian trace, but we have some sigma times sigma transpose. Here, sigma is a matrix value function. So it can be any matrix value function. So yeah, so it's somehow describing the correlation between dimensions. So we can choose sigma based on different equations. So the key is still that in this equation, we encounter computing the full Hessian. So the full Hessian will be very expensive. And we are going to use Hutchinson trace estimation to replace the Hessian trace part. So let's talk about some technical details. So previously I talked about Hutchinson trace estimation, and I showed
Zheyuan,
that. Okay.
this is Sapu
Yes.
from Davis. So I had a question on on HTE itself. I just looking at
Yes.
HTE, I feel that is there a connection between what HTE does and in quantum mechanics for Schrodinger, for example, often people use the density matrix to compute the eigenvalues and eigenfunctions. So there's some connection there because it's very similar, at least. I'm looking at it, just looking at it. I don't know the exact connections, but it's reminded me of that instead of solving the Schrodinger eigen problem, right? There's another way to extract the same information is through the density matrix, and then also you use there's basically a formula for the trace or something. So that was one connection. The other question was that when you do the unbiased estimator, what is the subsets I and J? What is the cardinality of those sets? How many? Suppose D is 10,000. Then how many entries are there in I and J? Is it random also, or you have to fix it, or what?
You said about the number of vectors, number of queries,
Yeah.
right?
Yeah.
Yeah, so I think this is somehow different. So if we talk about PIN, the key is that we want to form an unbiased gradient estimator to optimize the model. So as long as it's unbiased, the model can be optimized. So in practice, we do find that the number of in my notation, it's upper V. You see in equation 11. So the number of inquiries will be the upper V. So in our applications, we found that a small upper V is enough for like one. It is somehow very small, but 10, like 1 to 10 is enough in practice. So I will analyze the variance later. So I think it's really depends on your also application. So go back to your question about the quantum mechanics. So density matrix is something similar because you know that exact density will be a function, the function rho x
exactly.
in quantum. Yeah, so it's infinite dimension. So to encode this infinite dimension function, we usually use some basis, which is the orbitals in the quantum mechanics setting, right? Like theta, costa, they all theta, costa, something like that. Coulomb equation. We actually use many orbitals to like project the infinite dimension function to some low dimension coefficient. So we project high dimension things to low dimension stuff. So this is, I think, is similar because originally we need to evaluate the full Hessian, which is D times D. That here D is the PD dimension, which is a very large. It is a very large matrix. But using Hutchinson trace estimation, we actually reduce the full Hessian matrix to a scalar. You can see that each entry, each query is only a scalar, so it's very cheap. 1 versus D times D or D squared. So yeah. So I think the difference is that in quantum mechanics, usually, if you want to get higher accuracy, you need more orbitals, right?
Sure.
Sure, but here we can use a very a very small number of inquiries or like orbitals, because here we are recursively optimizing the pin. It is an optimization. We have many epochs, so we can use one query at each iteration, and then we optimize for many iterations. Then that's okay. But in quantum mechanics, the number of orbitals are fixed at the beginning. So I think that's the difference.
Yeah, also, another related question is that if you take a Laplace equation, like the Poisson equation, like what you took, right? So, and in
Yes.
higher dimensions, then let's assume that, in some sense, if all the dimensions are sort of similar, like you have sine functions, for example, so just a product of all sines, for example, right? Let's say. So there's no, the behavior of the function is sort of invariant to how you label the dimensions. So all the dimensions, look to be the same in some sense. The behavior of the function is, you can swap x and y or z, and it becomes the function does not change basically. So,
Right.
I'm just trying to get a sense of, if suppose some dimensions are more important, there's more, variation of the function in that dimension. Does that impact how your solution, how the strategy works, or is it invariant to that? I don't know if I was clear or not in my question, but just that I was thinking that if the locality or the gradients are very large along one direction only, right, and in the remaining directions things are very, very nice and well behaved, then does that impact the algorithm or the approach?
Sure. So in some cases, if we have a variability, we have many difference in different dimensions, then this kind of method will for sure we will need to have a larger batch size. So it's really something like trade-off, just like in traditional pin training in low dimensions. In some areas, the points will be more important. So there's some adaptive sampling strategies,
Sure.
like adaptive weights. Yeah. So
Yeah.
I think in this work, we are not considering, we are somehow considering the anisotropic, we call anisotropic solutions, but we do not take extreme anisotropic solutions. But we can, if we face extreme anisotropic solution, then we can also do some adaptive sampling or importance weighting on different dimensions during optimization. If we
Yeah,
detect,
thanks a lot. You can continue. Thanks a lot.
yeah, so I think the choice of V also depends a lot. I will analyze the variance. So we have many choices of V, and to minimize the variance, and maybe some problems prefer this kind of V, and another kind of problem prefer another kind of V distribution. So I think this is a somehow very interesting problem. Yeah. So beyond maybe something that beyond. So, but this is a very good question. Thank you. So. Do you have any more question?
No, I'm good. I'm good. Thanks a lot.
Okay, thanks. So, so I would just want to talk about the trace of V. So I mentioned that Hutchinson trace estimation is okay with all V if it's the expectation of V times V transpose is identity matrix. So there are actually numerous traces. So in classical mathematics setting, to minimize the variance of Hutchinson trace estimation, we usually opt for the radiometric distribution as follow. So for each dimension of the vector V, it is a discrete probability distribution that has getting -1 and +1 with half-half probability. So it's somehow discrete. Yes. So yeah, so this is called radiometric distribution. And intuitively, if we choose 1 and -1, then you can see that on the diagonal it will be, because 1 times 1 equals 1, -1 times -1 also equals 1. So the variance on the diagonal part will be diminished, but on the off diagonal part it will have some variance. So this is something that classical results to minimize the variance of Hutchinson trace estimation. So the idea will be the same. So I will go to some technical details. So before that, I just mentioned that I just want to remind that here to save notation, I call this Hessian trace part as A. So A is the main bottleneck, and B will be the rest. So B maybe include the time-dependent part and also the nonlinearity. Here, F is a known function. It can be any nonlinearity, like in Black-Scholes equation, maybe Black-Scholes equation can be some nonlinearity related to the options. It depends on European options or American options. It corresponds to different nonlinearity. In Hamilton-Jacobi-Bellman equation, it is the square of the gradient of U. So so different equations correspond to different nonlinearity in F. But the key is that F only includes the first order derivative, and the main computational bottleneck is still the Hessian trace part. Okay, so with this notation, we can similar to SDGD, we can replace the original expensive pin residual with a randomized HTE estimator. So we plunk the HT estimator into pin loss. So the original pin loss will be something in equation 13. So we use the full Hessian. So to compute 13, we need to first compute the full Hessian, which is a D times D matrix. So it will be very expensive. You can imagine that D times D matrix, like if we have thousands or millions of dimensions, then this matrix will be just unrealistic to compute. And we can use Hutchinson trace estimation to replace the full Hessian. So in equation 14 and the last equation, we have the biased and unbiased part. So just like SDGD, if we need to have some different sampling, two classes of sampling, VI and VI hat, to make the loss function unbiased. And equation 14 is biased because the nonlinearity of mean square error loss. So this is the HTE loss. So I will go to some advantage of HTE. So just as I mentioned, we reduce the full Hessian to Hessian vector product. Hessian is a D times D huge matrix, but Hessian vector product is just a scalar. So we reduce the memory cost significantly. Another thing is very good is that the Hessian vector product of a pin can be computed efficiently via Taylor mode auto differentiation in JAX. So as you know, JAX is very efficient in automatic differentiations, and it's something like very popular in scientific computing. So it's a coincidence that maybe not coincidence, but Hessian vector product in the Hutchinson trace estimation can be seamlessly combined with the Taylor mode autodiff. So Taylor mode autodiff is especially good at computing the high order derivative. So here we have two second order derivatives. So it will be very efficient. So Taylor mode autodiff avoids the conventional stacked backpropagation, backward mode autodiff. So it's tailored for something like high order derivatives. But also the original mechanics is very complex. It is related to the design of JAX, and we actually explain something in our Hutchinson trace estimation paper. But high level speaking, just to give you a high level impression, so Taylor mode AD's acceleration comes from the structure of high order derivatives for nested function via the Faraday-Bromo formula. So you can imagine that we have a chain rule for the first order derivative when it was taught in the class in the undergraduate calculus course. So basically, we can extend the chain rule for high order derivatives with nested function. And you know that neural networks are nested functions. So if we write down the nested, functions high order derivative expression and encode it as an prior knowledge into the autodiff, then it's very more efficient than viewing the function as a black box, and then we call a backward mode autodiff recursively, which will incur a lot of costs. So this is the high-level picture of why Taylor mode automatic differentiation is good. So I will show you some code. So we open source our code in this GitHub repository, and we here in our paper in this slide we provide a pseudocode for your understanding on the implementation. So in the implementation is really important because, as I mentioned, Hutchinson trace estimation is a Hessian vector product. So if we stupidly compute the full Hessian and then do the vector times Hessian times vector, then it will be no good thing. So it's important to use the Taylor mode AD. So in this code, we have a trace function, trace fn, and we have a random Rademacher vector. So we sample the random Rademacher vector, and then we have this using JAX, the jet jet modulus to compute to set up a Taylor mode autodiff, and then we input the radiometric vector into the Taylor mode AD, and then we can got the Hessian vector product. So I understand that this code maybe you may don't understand why we can compute it directly via jet, but you can find some, it is actually explained in the JAX handbook. So I just want to show you that the implementation is very, very straightforward. So it can be plugged in use, and with this code part, if you want to solve some high dimension PD, you can just put this part. Also, I provide the full code in this GitHub repository. So yeah, so after talking about code explanation, I would like to unify SDGD and Hutchinson trace estimation. They are actually connected. So we can actually view SDGD as Hutchinson trace estimation too, with a specific trace of the V distribution. So we compute a discrete distribution PV such that V equals square root D times EI. So here D is the dimension and EI is the standard basis vector with 1 on the ice coordinate and 0 elsewhere. So it is very easy to check that this distribution satisfies the assumption of Hutchinson trace estimation. And if we plug this kind of distribution of V into Hutchinson trace estimation, then we get SDGD. We are sampling dimension to estimate the Hessian trace, which is if we want to estimate the Hessian trace, we randomly sample different entries on the trace on the diagonal to estimate the trace. So one difference is that in SDGD, we sample dimension without replacement, which means that we sample one dimension at most one. But in HTE, it may be different because HTE can sample with replacement, but it is relatively a minor difference. So this is very interesting. So you may wonder that I mentioned previously that classical mathematician view the previous radiometric distribution as minimization of the minimizing the variance of HT, but actually SDGD's choice of distribution also minimize the variance. Just like this minimization is not unique. We have multiple traits of distribution V to minimize the variance, and HTE is the classical choice, and SDGD is something like new choice. So yeah, so I think why classical people don't mention this SDGD trace of distribution is that SDGD is a discrete distribution. So it is something like you can only have at most D trace. You are picking D vectors, but in previous Hutchinson trace estimation, it's we can recall that. So in Hutchinson trace estimation, each entry of V can be 1 or -1. So there are very many traces. It is somehow grow exponentially. The trace of V actually grow exponentially. So SDGD, the trace of vector is only D, so it's grow linearly. So this is difference. So this is something different. So I will compare the variance of SDGD and HTE in trace estimation. So our goal is to estimate the Hessian trace. So A here can be the Hessian in pin also. So SDGD's estimator, you can see that its variance comes from the variance between diagonal elements because we're picking some diagonal elements and compute a mean to estimate the mean of all diagonal elements. So its variance comes from diagonal elements only. So that's the previous question. This answers the previous question. So if different dimensions can change rapidly, then SDGD may have a huge variance due to the difference between dimensions. But HTE is another interesting thing. So we can compute that HTE's variance. You can look at the second bullet. So HTE's variance only comes from the off-diagonal terms. So as long as the off-diagonal terms are small, HTE is very exact, even if we have difference in dimensions. So this is something very interesting because SDGD's variance comes from diagonal terms, but HTE's variance comes from only off-diagonal terms. So this comes to a trade-off. So in this slide, I will have some simple conclusions that maybe answer the previous question. So if the diagonal terms are similar, which means that the PD exact solution is symmetric or isotropic, then SDGD will have a very low variance. And if on the other hand, if the off-diagonal elements of the Hessian are 0, which means that if the PD exact solution is in its different dimensions do not interact, then HTE will be very accurate. So HTE can also fail if the scale of off-diagonal terms will be large. Then HTE, since its variance comes from only off-diagonal term, then its variance can be large. And in this case, SDGD will be better than HTE. So there's no, you cannot draw a conclusion that, okay, there's no good, better one. So I mean, it only depends on your setting. So if it depends on your setting. So if you care about variance between dimensions, then you can consider HTE. But if you worry about the off-diagonal terms, then you can use SDGD. So this is something like the advantage and disadvantage. And also, I would like to compare the generality because they are separate papers. So I would like to use I would like to say that SDGD actually contains a more general philosophy. So if we encounter a future high-dimensional problem, then the key observation is that we can decompose the gradient or the optimization of the algorithm into dimension pieces, and then we can sample part of the dimension for update. It's a very general philosophy, but in Hutchinson trace estimation, it's mainly for second-order parabolic equation. So it's general enough, but it's more like it's designed for this kind of second-order parabolic equation. Also, it can cover a lot of interesting cases. So yeah, so I will go to some computational experiments. So comparing HTE, SDGD, and also vanilla pins. So I would like to design some exact solutions which have difference in different dimensions. So you can see that I designed a two-body interaction solution and a three-body interaction solution. This is to ensure that our exact solution is effectively high dimension. So it cannot be decomposed into low-dimensional parts. Otherwise, it is not interesting. So the problem is effectively high dimension. Also, we have coefficient Ci. Ci is stored randomly from the Gaussian. So there's difference between different dimensions. And also, I will define the PD problem on the unit ball. So as you can see, the multiplier 1 minus the square of norm of x is for a zero boundary condition. So we don't want the boundary condition to affect our comparison because SDGD and HTE are mainly randomly estimating the residual. So we don't want the boundary to convey some wrong message. Also, in high dimension setting, it is important to maintain a low, it is something like trivial boundary. Otherwise, the boundary is actually d minus 1 dimension, the unit sphere. So if we have a non-trivial boundary condition, then training on the boundary may enough. So it is important to maintain a zero boundary condition for fair comparison. So we want to focus on the fitting of the residual. So we consider a nonlinear sine-Gordon equation with a sign nonlinearity. In our original paper, we also compare linear equation like Poisson equation and also alien-Kant equation with polynomial nonlinearity. But in this slide, I will only use this sine-Gordon equation. So here there are some results and also some settings. We use an NVIDIA A100 GPU with 80 gigabytes memory. So it's a relatively large, very large memory. And we choose 100 residual point in all high dimension, and hyperparameters are kept the same. I mean, I want to compare these algorithms fairly. So the network will be a 4-layer network with 128 hidden units. And for SDGD, it samples only 16 dimensions. And for HTE, the number of queries upper V is 16 to ensure that SDGD and HTE has a similar cost to compute them fairly. So in table 1, I show some results. So maybe we can look at ping first. So you can see that the memory cost of ping actually grows drastically. So in 10,000 dimension, ping will fail. Its memory cost is relatively growing fast. And also you can see the speed. The speed is iteration per second. So you can also observe that like in 5,000 dimension, it can only run 8 iteration per second. So we optimize for 10,000 iterations. So it's about like 2 hours. So yeah, maybe half an hour to 1 hour. Sorry, it's 1 hour, so it's very slow. But if you look at SDGD and HTE, it's very impressive. if you look at the memory cost, you can see that the memory only grow slowly with respect to dimension. This is due to the fact that we are sampling dimension, and the sample size of dimension and also the query size of HTE are kept the same among all dimensions. So the memory cost actually only grow very slow, and the growth can come from the growing size of network. You know that at least the input size is larger in higher dimensions. So the memory cost still grow in SGD and HTE, but very slow. And the speed is also very impressive. So the speed is we can see that it's linear in dimension. And in terms of performance, arrow 1 refers to the relative L2 arrow for the two-body interaction in the previous slide, and the arrow 2 is the results for three-body solution. So the key is that in lower dimension, like 100, 1000, and 5000 dimensions, the convergence results of PIN and SDGD and also HTE are similar. So there's no harm if we sample dimension or use Hutchinson trace estimate. It can still converge to a relatively good point. And in higher dimension, it is also very interesting because in higher dimension, PIN directly fail. But we can see that HTE and SDGD can always get a lower, very low relative L2 error. And if we compare HTE and SDGD's performance across different dimensions, we can see that it's relatively stable. So we do not observe some curse of dimensionality in high dimension. Sample part of the dimension or using part of the query for Hessian trace estimation is actually enough. This is actually in accordance with our previous philosophy that so in low dimensional PIN or even the broader class of machine learning community, like we only sample a small subset of data for one gradient update, but even if we sample part of the data or part of the residual point in each iteration, we can still get a good result. So here, the philosophy is the same. Although the power dimension is high, we sample part of the dimension or use some query to like project a high dimensional Hessian into some low dimensional basis. It's still enough as long as it is unbiased and we are optimizing towards the correct part. We can view this kind of SDGD and HTE as an extension to our classical SGD over points. Yes, so here's the first experiment. And for the second experiment, I would like to compare with some no-pin baseline, because before our paper, there are some other papers. There are no non-pin results, but they also focus on high-dimensional PDEs, and they are usually tailored for second-order parabolic equation. So they cannot do the sine-Gordon equation because it's time independent. So we would like to claim the generality of PIN with SDGD, but in this experiment, we just want to test if PIN can outperform this classical method. And we know that PIN is more general, so that's why we can claim that we can somehow, to some extent, solve the curse of dimensionality. So we adopt their other non-PIN baseline settings, and one famous baseline will be BSDE, which is backwards stochastic differential equation. Its full title is Solving High-Dimensional PDE with Deep Learning, published on PNNS in like 2018. So they can only produce the prediction on one test point at each training instance. But as you know, PIN is mesh-free, so we can predict many test points after one training instance. So that's another advantage of PIN. So we will use some nonlinear equations whose exact solution will be unknown. So previously we designed a fabricated solution and then plug it into the equation. So in this case, we do not know the exact solution, and it will be highly non-trivial and non-separable. So the reference value of these PDEs on this test point will be computed by a multi-level pickout method with sufficient theoretical guarantee. So multi-level pickout method is also some method tailored for second-order parabolic PDE, and it cannot work for general PDEs. And another thing is that we need to sample the residual points of PIN based on SD trajectory, because these kind of equations is defined on the whole domain. So here I show these PDEs with different nonlinearity, with alien-Kahn equation, semi-linear heat equation, and sine-Gordon equation with different nonlinearity, and also with some initial conditions. And you can see that here, X is in the entire D-dimensional domain. So sampling of residual point is very important because in low-dimensional spaces, it's bounded. So we usually uniformly sample over the bounded domain or adaptively sample over the bounded domain. But here, the domain is the whole domain. So we need to sample the domain, sample the residual point cleverly. So here is the sampling method in equation 16. So the key is that these kind of second-order time-dependent parabolic equations are related to some class of stochastic differential equations. And specifically, they are related to a simple Brownian motion. So you can see that the second-order part is Laplacian. So Laplacian corresponds to the Brownian motion. So you can see that in equation 16, it is actually sample from a Brownian motion. So you know that the Brownian motion evolves like t times the variance is linear in t. So it is basically a Brownian motion. So we sample the points from the Brownian motion. So and then train the pin. So here is the results, and we only used one test point.
Hi, Zheyuan, one question, just to make sure I understood. So you said that for this case, since you know the shape, the form of your equation, you're imposing like some kind of PDF to sample your points, to sample your dimensions?
No, we do not have any like prior knowledge on the dimension. We just sample it randomly. We do not do any adaptive stuff on the sampling of that dimension. But I mentioned that these kind of equations, PDEs, are actually connected to SDEs. So so it is not related to some distribution. So high level speaking, it just affects the choice of residual point. Yes, so there is some classical theory for this kind of equation, saying that okay, they corresponding to some stochastic differential equation, and then we can have some stochastic, so we can use this connection to solve them. This is some classical method, and also the previous papers on high dimensional PD, so they can only solve these kind of stuffs. Yeah, so maybe there's a confusion. So I just want to emphasize that the connection between PDE and SDE only affect the choice of residual point. Because as I mentioned, the domain is the entire domain. So we cannot, there's no idea to sample. So we need to leverage the connection between PDE and SDE to sample the residual points along the SD trajectory. Also for classical method, they also sample training points along the SD trajectory because of the connection between PDE and SD. So yeah, so this is just about the sampling of residual point. So yeah, so in this table, I show some results. So I compare with many baseline. The first is the forward-backward stochastic neural network, and the second is the BSDE, the famous paper on high-dimensional equation, but actually we beat them. And the third is the deep splitting method. Also, it is maybe the previous best paper because it can scale up to 10,000 dimensions. So we can see that with this kind of trace of residual point, we can actually train a pin with better accuracy. So pin can also do something that previous methods can do. But as I mentioned, pin can also do more, like general PDEs, like time-independent PDEs, like Poisson equation and on the bounded domain. And it can also do this kind of PDEs, time-dependent parabolic PDEs on the unbounded domain. So this slide actually demonstrates that pin is versatile. It can do something previous method can do with higher accuracy. It can also do something like previous method cannot do. And its generality over all PDEs is just demonstrated. Yes, so we also have some more experiments for the Hamilton-Jacobi.
Zheyuan, can you show at least one comparison with Hamilton-Jacobi, because we have Bellman, because we have people in the audience who are interested in this. Hamilton-Jacobi Bellman.
Yes, maybe I need to change my screen sharing. Sorry for that.
Okay.
I need to find that comparison. Sorry for that. And during preparation, I'm considering that we may do not have time, but I will find out these results as soon as possible.
You have time.
Yeah. So yes, I have downloaded my paper and I can share the screen now. Yeah, so this is our paper, SDGD paper. So so in one experiment, we actually compare with the basically in our paper, we do more ablation studies to understand like the trace of sample dimension, batch size, and more. But in this presentation, we do not have enough time to cover every study. So actually in our original paper, we consider this HJB equation with linear quadratic Gaussian control with this nonlinearity. So you can see that it is also a kind of second order parabolic equation. So the good thing is that we can obtain its exact solution from Monte Carlo. So this equation is, or this setting is actually very classical because many previous papers, also famous previous papers, adopt this setting. So yeah, so we choose, so here's a cost function, the gx is a terminal condition. So in Hamilton-Jacobi, we use terminal condition. So the gx, usually we choose gx using like the logarithm like cost function. And it is actually something not a very impressive part because you can see that along different dimension, it is symmetric. So it is isotropic. So it's less challenging. But so to test this, to test the performance, we also design a non-convex Rosenbach cost. So this cost has some random coefficient to make it not symmetric, and also the cost function will not be will be more complex like non-convex. So I understand that maybe this cost function is not realistic, but we just want to test the performance. And in this case, we actually compare with another two baseline. The first is Wang. So there is L2 pin suitable for training, is L2 loss always suitable for training pin. So in their paper, they show that for HJB equation, we need to use a technique called adversarial training. And this adversarial training is very costly. We need to take an additional derivative with respect to input. So the PD is two second order, and we need adversarial training. So the method will be third order. So it's very costly. And another baseline is he. So he actually proposed another kind of method for high dimensional pin acceleration, but it is less, it is more restricted. And also you can see that we actually adopt their setting to compare with them fairly and use all PyTorch like implementation. And also these results are directly taken from their paper, and the time are also taken from their paper. And we can see that if we sample dimension, we can finish the training much shorter, much shorter time. And in their original paper by Wang and he, they can only go to 250 dimension, but we can go to higher dimension, like 1000 dimension. And I try to test this previous method in 1000 dimension, and they require more than 5 days to converge. So this is not a realistic time, but we can converge in like less than 4 hours. So we can also go to higher dimensions, and where Wang and his method actually directly goes out of memory, but we can still at least train it. So this is for scale up, like previous method directly failed due to the huge amount of differentiations, but our method is good. It can scale up for training. So this is about the Hamilton-Jacobi-Bellman. And another thing I would like to, this is original Hamilton-Jacobi-Bellman. Another thing I would like to talk about briefly is that about our recent paper called score-based pin. So in this score-based pin, we also solve high-dimensional Fokker-Planck equation. So we show that Fokker-Planck equation solve for a density. So in Fokker-Planck equation, it describes a density, a probability density. So we solve for a distribution. So if we solve for the log distribution, which is the log likelihood, then Fokker-Planck equation becomes HJB equation. So once, well, if we, I want to talk about Fokker-Planck just because they can be transformed to Hamilton-Jacobi-Bellman. So in this score-based physics-informed neural network, we also use the Hutchinson trace estimation to solve these kind of Fokker-Planck, and you can also call them Hamilton-Jacobi if we solve the log likelihood. And we also show that this kind of Hutchinson trace estimation as SDGD are very impressive in solving Fokker-Planck, and also it's related Hamilton-Jacobi. And I think the terminology is that it's called controlled diffusion Hamilton-Jacobi-Bellman equation. So basically, this kind of problem correspond to Fokker-Planck equation, and also its corresponding stochastic differential equation. So although I do not have the time, I just want to talk about it a little bit. And if you are interested in this paper, you can also download it and have a look at its connection with HJB equation and how our score pin how can the score pins perform better than the previous approach, which is adversarial training. yes, that's about Hamilton-Jacobi-Bellman. Yes. And I think sorry, I think that's all for my presentation. And here's the conclusion. So we have presented SGD and HTE to scale up and speed up ping for very high dimensions. So our result, especially like millions or thousands of dimensions, and our result demonstrate that this method can avoid curse of dimensionality to some extent, as Bellman first defined it. We compare them thoroughly from their generality and accuracy, and we show that SDGD plus ping can outperform previous best method and also do something that previous method cannot do. Okay, that's all for my presentation. Thanks for your listening, and any questions are welcome.
Thank you so much, Zheyuan, for your great talk. However, you've asked many questions so far, but now officially I open the floor for questions. Do we have any questions for the speaker? I think Suku have question.
Yeah, so thanks a lot.
Oh.
Very nice talk. Very interesting indeed. I had like 2 or 3 related questions. The first one is you showed L2 errors, right?
Yes.
Did you also look at the H1 error just to see how the gradients are?
Actually, so it depends on your application. So if we talk about this kind of nonlinear second-order parabolic equation, we usually care about the L2 error.
Right. I was talking just a Poisson equation. If you just do a Poisson equation, right? And then you can look at H1 and L2, for example, right? That was the observation. And the other question was that you solved mostly, is it most of the problems on a hypersphere, or can you also solve something on a hypercube?
Sure, sure. But hypersphere is one example, and we also saw PDEs on the entire domain, like also the Hamilton-Jacobi-Bellman equation.
Right.
RD, right? RD, yes, you can see that here is RD. So in this case, we sample residual point based on unit Gaussian for field comparison, because previous paper use unit Gaussian. But I think a better method is to leverage this kind of PDEs, the connection with SDE, so we can still sample based on the SDE trajectory. So also, because it is a Laplacian, the Hamilton-Jacobi-Bellman equation corresponds to a vanilla Brownian motion, so we can sample residual point on the Brownian motion for sure. Yeah, so I think the on the entire RD domain will be much challenging, and it is something that will be surprising. So I think the future work will be, maybe we can prove some results to prove the convergence of ping on this RD domain, because previous papers, also I have done a ping theory paper. In this ping theory paper, we really focus on the bounded domain, especially for lower dimension problem like fluid mechanics and also other applications where the domain is bounded. But the surprising thing is that we can use ping to solve unbounded PDEs defined on unbounded domains. And to the best of my knowledge, I don't find any reference to prove that. Also, in Wang's paper actually proved that L2 loss fail, but their proof is still based on a bounded domain. But actually, they solve an unbounded problem. Yeah, so I think that's about the domain.
Yeah. Also, how do you impose the condition UXT is equal to G in the ansatz itself? Because
yeah, so in all of these cases, we usually use the encode the terminal condition, or you're using the Dr. Lulu's paper with hard constraint.
Okay. So you just use G itself in the ansatz, right? Basically.
Yeah.
Okay.
So that we can know the information of its derivative. But one thing is that if G is non-smooth, then it's better to use vanilla boundary loss. Because if G is non-smooth, then ping encodes some high order derivative, but we cannot compute the high order derivative of a non-smooth terminal condition or boundary condition. So this is one thing to note. And actually in the scoping paper, I have something like this. So because I have a non-smooth, so in one experiment, I use this kind of stuff as my initial condition. It is the Laplacian distribution. So you can see that this boundary, this initial condition is non-smooth, right? So in this new paper, I mentioned that since the Laplacian probability density function are non-smooth, we do not hard constraint the initial condition. But in other cases, we just hard constrain it, because we can know the boundary condition or initial condition itself, and also the information of its derivative. And I think it is very important for high dimensional ping. Also, in low dimensional cases, we usually use 2 loss, but in high dimension, it is recommended to hard constraints these kind of boundary or
Sure.
initial condition.
Yeah, I asked the question because, on a hypersphere, you can always take 1 minus the norm of x squared if the boundary condition is going to be 0 on the boundary, right? But if you take a hypercube, then all the dimensions are separable, right? So then it becomes challenging if you want to impose 0 on the boundary, right? For example, if you take a hypercube, right? So then it's more, it's difficult, right? And the last point I wanted to ask you is that, now, if you, instead of is there a notion of a unbiased estimator for the variational form? I mean, you know what I mean? Like if you don't take only one derivative is like an integral. Suppose you have an integral of u, right? Which is involved, right? U prime square or something. Can one construct something which is like a estimator for that? Because then you'll need only one, if it's possible, of course, I'm not sure. But if that is possible, then you'll only need one derivative also in your whole computations, right? Because you were talking about the cost of derivatives is really is a bottleneck, right? The more derivatives you need is
expensive.
Yeah, autodiff is expensive, right? So therefore, I mean, is there a notion of doing an unbiased estimator for an integral in some sense, right? Rather than just a loss which is a least squares, discrete L2, right?
Yeah, I think some related work.
Yeah,
I think related will have done. So we also have an example of Schrodinger equation. So we solve it in the variation form. You can see the loss function. But in that case, we actually use a specific network architecture called separable pin or tensor neural network. So we use this kind of model structure to make the numerical integral cheap. So we can compute dimension-wise integral and then compute the product to replace the original curse of dimensionality grid.
Yeah,
so,
that was my next question was that actually on how do you do the integral step, right? Of course, if it's not separable, you can't do it, right?
Yeah, so I think another approach is to use normalizing flows, because normalizing constant can be computed efficiently. So that's another kind of future work. But I think in solving Schrodinger equation, as you know, Schrodinger equation try to solve some density. So here the phi is also a density. It is normalized. So that's why we have a normalization in the denominator. So we can also use normalizing flows because it's tailored for distributions or density. So this is also another choice, but I haven't tried normalizing flow yet. But I think tensor neural network or separable pin can be good. And also in this experiment, we combine SDGD with this equation to show the generality of SDGD, because it still includes the first order derivative, and this phi can be an expensive model to evaluate because it's separable. So we have dimension-wise model. So we have these separate models, so it can be very expensive. So that's why we sample dimensions to alleviate the computational burden.
Okay, thanks a lot. Very nice work.
Thank you. Do we have any other questions for the speaker? George, do you have any comment?
No, Zheyuan did a good job. I have a comment, yes, that I will go around after this is done and ask people to explain to me how we tackle the high dimensionality. In other words, to explain to me the talk that Zheyuan gave. So I will do a little quiz later.
Thank you so much. So I think it's time to close the first session. So it's time to move on to the second session, our second talk. Thank you so much, Jan, for your great talk. And Dr. Wang, can you hear me? Our second speaker.
Sure, can you hear me?
Can you share your, yes. Can you put it on presentation mode?
Yeah, one second. One second. Okay. How to do that? I'm not familiar with Mac /show. Okay. How about that?
Yes.
Good.
Yeah. Thank you so much. So our second speaker is Sifan Wang, He will be giving a talk on PirateNets, physics-informed deep learning with residual adaptive networks. Dr. Wang obtained his PhD degree in applied mathematics and computational science at the University of Pennsylvania in 2023, advised by Professor Pardikaris. His research interests lie in the intersection of machine learning, scientific computing, and computational physics. He is particularly interested in developing scalable and robust machine learning algorithms for solving partial differential equations and leveraging these to solve problems in science and engineering. With that short introduction, the floor is yours, and you can start your presentation.
Okay, thank you. Thanks the host for the invitation and the nice introduction. My name is Sifan Wang, and I'm very happy today to present my latest work, PirateNets, in Crunch seminar. For this work, it's actually more about the pins, physics-informed neural networks. But I believe the insight we get from this work can be easily translated and used in the general purpose of physics-informed deep learning. More specifically, we want to answer this question in this work. That is, how can we train deep pins effectively? Actually, this is a fundamental question in deep learning community, how to train deep neural networks. And in fact, why this question is fundamental, if you look at the most impressive and successful application by deep learning, they are achieved by training deep large models with big data. And in fact, there are lots of works focusing on this topic. The representative example is ResNet, with no doubt, proposed by Kai-Ming. It turns out that this skip connection can effectively prevent the degeneration of deep neural networks. Another good example is Transformer. This architecture is very scalable in the sense that you can simply use very large and deep transformers to digest huge amount of data. But if we go back to pins, for this question, unfortunately, we don't have a clear answer yet. So this is a key question we want to answer in this presentation. So please keep this in mind. And let's start with a brief overview of pins. So I believe many of you here are quite familiar with the introduction to pins, so I'll keep it quite short. Let's restrict us to the setting of solving the forward problems. Suppose that we have such a problem set up. We want to solve this general PD system, where n is a differential operator, which can be linear or nonlinear. And here B denotes a boundary operator, which can be Dirichlet, Newman, or Robin, whatever. So we want to use pins to solve this PD system. Then we just simply represent the solution U by a neural network, which takes the coordinates x and t as inputs and outputs the predictions corresponding to those query points. Then if you use a smooth activation functions, then such a neural representation is smooth. Then we can compute these derivatives using automatic differentiation. Here, YAD instead of numerical differentiation. There are several merits of AD. The first thing is that there's no numerical errors due to the discretization. And such a issue becomes more problematic when we need to handle complex geometries. Second thing is that this AD is really convenient and helpful, especially when tackling the high dimensional PDs, just like the first speaker demonstrated. So these are the merits. But if we go back to our goal, we want to solve this PD, then based on this system, we can formulate property constraints. For this PD, we can formulate two terms. The first one is called a PD residual loss, denoted by LR of theta. This loss aims to enforce a network to satisfy the PD within the domain, and we call XRI those points as collocation points. These points can be randomly sampled in the computational domain, or can be directly a fixed mesh or grid. For the second loss, we have this boundary condition loss. the purpose of that is to enforce the network to fit the boundary conditions. Then after training, we may expect that these losses can decrease to some small value. Then those constraints are satisfied approximately. We may expect that our pins can give us desired approximation to the PD solution. This is the pins framework. But in the next slides, I want to demonstrate that the vanilla pins actually are not scalable. Here, the scalability doesn't mean we cannot afford the computational costs to train deep pin models, but means that we cannot gain benefits from training deep pin models. And in fact, if you look at the pins literature, if you check their hyperparameters, you'll see that actually we are using quite small networks, typically less than 10 layers. In general, actually, they are 4 to 8 or 10 layers, hundreds of neurons per hidden layer. If you count the number of total parameters, they are generally about 10,000s or 100,000s. They are quite small, actually, compared to the those big, large models used in the computer vision or NLP. But in the following slides, you'll see that it's not because we don't want to use large pin models, but simply because we can't. To demonstrate this, I prepare an example, a numerical example. The Allen-Kane equation. This is a well-known benchmark studied in the recent pins literature. What happens if we train a pin model to solve this equation? Here I show the resulting relative errors after training. So if you look at this blue line, this means that this represents the results of training pins with MLP as backbone. You can see that deeper MLPs yields greater test errors. Okay, you may argue that this is well known. Deep neural networks are harder to train, and the people have solved that, just like the ResNet you mentioned. All right, that's a good point. So we test the ResNet. We test the vanilla ResNet by replacing MLP by this ResNet and keep all the hyperparameters the same. Run the same experiments. The results are demonstrated in this light green curve. You can see that this ResNet, we can get better accuracy slightly, but we cannot convert the trend. Still, we get worse accuracy when we're increasing the number of hidden layers. In other words, adding skip connections cannot solve this scalability issue. But instead, if you look at this red curve, that's the results corresponding to this PirateNet I'll introduce in the following slides. You can see that the PirateNet can gain accuracy from increased depth. This is really something fundamental we need if we want to scale our architecture. But before introduce this architecture, we need to understand why such an issue happens, why pins suffer from the scalability issue. With this end, we need to revisit the pins loss. So remember, we have this problem set up, and we have this loss function. So if you look at it, you may have propose such a claim. Basically, if the training loss converges to 0, then the derivative networks will converge to the corresponding solution derivatives. Basically, the role of those PD residual loss not only enforce the network to converge to the solution, but also regularize the behavior of the network derivatives. More specifically, we may give such limits mathematically. Of course, such claim cannot hold for very general PDs, and actually this is related to the higher order estimates of pins. But in the next slides, I will show that at least for some classical setting, we can rigorously prove such a claim. So the first theorem I will introduce is about the second order linear elliptic PDE. We give such a notation. Here, D is a differential operator, where the coefficients Aij, Bi, and C of x are smooth. And we also assume that this D is uniformly elliptic. Then we can prove this proposition. Basically, if we define such a loss function in a continuous sense, we can prove list inequality holds. There are several remarks I want to give. The first thing is that list inequality is sharp in the sense that we can only get an index of 2 here given the current loss function. Why this 2 is important because we want to take actual gradients up to the order of the PD system. Another thing is that this list inequality only holds locally in the sense that for any complex set V in the domain omega. Basically, this is an interior estimate of the pins. And unfortunately, we cannot give a global estimate. The reason is because we lost some regularities due to this loss, boundary condition loss. And similarly, we can prove some results for the second order linear.
Sifan, the estimate, I think we have estimates, some of our papers in the H1 if you include the
yeah, H1 is doable, but if we want to get H2, then we cannot get H2 for
yeah, but that's known even for finite elements. That's standard.
Yeah. Can I continue? Okay.
Yes,
Sifan, I had a quick question.
Yep.
This is Suku here. So what is how do you do, like, how big is the set V?
We can be,
do you have a sense?
Can be very close to the omega, as long as it's a compact set. So basically,
Okay, but
lose something near the boundary.
Okay, but you can't, the result is not true for omega. That's what you wanted to emphasize, right?
Yeah. We cannot extend this inequality to the exact boundary.
Okay, so as George was asking, I mean, for the estimate in H1, you have something similar, or basically
for H1 we can prove that list inequality holds for the whole omega.
For whole omega. Okay.
Yeah.
Okay. Because often for second order PDs, we are by and large interested in U or the gradient, and like was mentioned that even FEM does not converge. It will converge, but you can't get estimates in H2, right?
Yeah. Okay, so let's.
Yeah. Thanks.
Okay, let me introduce to another theorems. That's about the linear parabolic PD. The results are quite similar. We can prove list inequality holds locally. Actually, the proof of list propositions are not too hard. They are just simple application of the existing PD regularity theories. Of course, we can prove more complex and general cases. For example, like a semi-linear elliptic PDs and so forth. But that's not the main purpose of list theorems. The main goal is to justify the claim we have. So basically, if you remember, we want to justify this claim. The convergence of training loss should imply the convergence of derivative networks to some extent, at least for some cases. Okay, so if you really buy that, then we have such an implication. The trainability of the derivative networks should determine the trainability of pins, right? That's kind of a necessary condition, but clearly not sufficient. If we have some trouble in the network derivatives, then clearly we have some troubles in the PD residuals, because the PD residuals is just a series of operations involving network derivatives. Then finally, we have achieved such a reduction. We can reduce the studying of PD residual networks to the studying of network derivatives. That's a kind of the first step. Okay. And then in the following slides, I'll review some pathologies at pins initialization. So to begin with, I need some background. Here is a forward pass of MLP, where WL are weight matrices, BL are biases, and the sigma just denote the nonlinear activations. Then if you remember here, what I present is the X-sphere rate initialization. Those weight matrices are sampled from a Gaussian distribution with a set of variance. And the list number is determined by the width of the L and L-1 layer. I want to emphasize that list variance is not randomly chosen. This thing is carefully calculated. The key purpose is to ensure the stable forward and backward propagation. You cannot randomly give another number, then this may break the trainability of the network. Then we can prove the following proposition. So basically, given the above setup, these things will hold at the initialization of an MLP. So the first thing we can prove is the first order derivatives of U theta is given by this product. The proof of that is quite simple. It's just by chain rule. But if you observe this formula, you can see that all weight matrices directly contribute to the final output, right? But if you compare to the network itself, in the previous slide, you can see that those weight matrices are hidden inside the activation function. And then you'll see that actually, if those weight matrices are outside, then and contribute to the final output, it will become very unstable. So basically, under some additional assumption, we can prove that this first order derivatives of network is approximated by this product. As a result, you can see deep networks are more vulnerable to vanishing and exploding gradients, right? Because for deeper networks, it's stable as if and only if the norm of each weight matrices are 1. Otherwise, it's unstable. As a result, this will lead to the unstable training process. Okay, then for B, actually, we can prove that if all the hidden layers have the same number of neurons, denoted by D, then the variance of the first order derivatives is bounded by the 1 over the width. This is independent of network depth. As a result, you can see that actually the first order derivatives is actually very close to 0. The one direct implication is that the derivative networks will tend to be a constant in wider networks, and this implying that networks closer to a linear function at initialization. So actually, if we solve a PD, right, clearly the solution may not be linear, then it means that the wider networks you use, you get a further initialization from your ground truth. This means plural initialization, right? So at the end of the day, I want to achieve such a conclusion. The conventional initialization schemes of MLP results in pathological initialization of derivative networks, right? Is there any questions about this proposition or any comments? Okay, then.
Yeah, so it's one question. So essentially, this part is saying that you have vanishing gradients, right? Your derivatives will become really, really, really small.
No, this is what happens at the network initialization.
Yes. But the idea is like here you're proving that the first derivative of U respect to X, that will become really, really, really small, because you have a really long network.
Yes, but I mean, during training, it may not hold.
Okay, but in that case, shouldn't that be addressed somehow by normal ResNet?
For that, I'm not sure. Actually, I cannot give you an answer. We need to regularly write down do the analyze, see what happens for the ResNet.
Oh, okay. Thank you.
Okay, this is a proposition. Next, I want to give some numerical support. So here we consider a simple regression problem. We have this target function, and we can generate the training data by uniformly sample xi's in a unit interval, and we can compute those yi's based on the formula we have. Here I just simply take 256 points. But something interesting is that we consider such a loss function. Basically, we change the different approximator, which is a network derivatives of different orders, right? So if we keep everything the same, only the approximator different, then the final accuracy of this regression test will measure the trainability of the network derivatives, right? So these are the results. Starting from left, this is the results showing what happens at initialization. Here is the variance of the first order derivatives at initialization. You can see for different activation functions, we get smaller and smaller variance for wider and wider networks. So this is really consistent with the proposition I showed. Moving forward to the second panel in the middle, this shows the variance of MLP derivatives of higher orders. Here we fix the activation function. You can see for higher order derivatives and for wider networks, we get smaller variance, right? Then moving forward to the last figure shown on the right, this is the result after training. You can see for deeper networks and for higher order derivatives, we actually have worse predictive accuracy. This really means that we get some trainability issue for higher order derivatives, and essentially we may get some trainability issues in minimizing the PD residuals. Okay, so with these results, we may have such a question: how to resolve this initialization pathologies of pins? Of course, you may think that, okay, all the issues are coming from this initialization I introduced. How about just changing that? Can we twist this initialization scheme, or say find a better initialization scheme to guarantee the trainability of both network and their derivatives? That's actually a good point, and actually I spent a long time towards this direction. But at the end of the day, I found that it's really it's really hard to balance it. In the sense that I can find a very good initialization scheme for the network derivatives, but somehow this scheme will result in very poor trainability of the network itself. So it's really hard. I can't say it's impossible, but it's really tough direction to try. But alternatively, we propose this architecture called the PirateNets that can solve the problem in a different way. So this is the architecture. This looks a little bit complicated, but in the next slide, you'll see it's quite simple. Starting from left, we have coordinate input coordinates. First of all, we project those coordinates into some cosine sine features. This embedding is called the random for features, and now it's widely used in the pins community. We know that this thing can mitigate spectral bias effectively. Then we create two gates from the embedded coordinates. These are just two dense layers and following nonlinear activations. Then we have this adaptive residual block. That's a core of this architecture, and I will introduce that with details in the next slide. Finally, we have this output is a linear layer of the XL. Okay, so let's take a closer look at this adaptive residual block. You can see, if you look at those equations, it's complicated, right? But if you remove those lines marked by different colors, you'll see this FL, GL, and HL, they are just three dense layers, okay? Then in the middle between them, we have two additional operations. I call it gating operation. This symbol represents pointwise multiplication. And then we have additional operation called the adaptive residual connection in this formula.
One question. The first the yellow lines are the modify MLP, right?
Yeah, exactly.
Okay. So
yeah,
in this, okay. So this time you added the blue line.
Yeah, the blue line is a key difference basically. But okay. I just want to make differentiate this from a standard MLP.
Okay, great. Thank you.
Yeah. So essentially, this adaptive residual block just consists of three dense layers plus two gating operations plus one adaptive residual connections. The key observation is as follows. Here we make this alpha L is a scalar and a trainable parameter. Actually, this alpha will determine the nonlinearity of each residual block. So if alpha is equal to 1, then XL plus 1 is equal to HL. This thing is fully nonlinear. But if alpha is equal to 0, then XL plus 1 is equal to XL. This is an identity map. And in the PirateNet, we always initialize all alphas at 0. And in the following ablation studies, you'll see this thing is very, very important. A direct result of this initialization is that since alpha is 0 as initialization, then each residual block reduces to an identity map basically those gray parts are completely gone at initialization. So the final output at initialization is just simply a linear combination of your coordinates embedding. Okay, and there's additional bonus for that. That is, we call it the physics initialization. So basically, we just simply initialize the last layer, this WL plus 1, as the solution to this least square problems where y are coming from some existing data sources. For example, it can be experimental measurements or solutions from surrogate model or solutions of the linear SPD, or if you only have the initial boundary data. In fact, actually, this ParaNet will offer you an optimal initial guess based on the available data in the L2 sense. There are some remarks. The first thing is that actually this initialization can be applied to any architecture as long as your last layer is linear, because any architecture can be viewed as a linear combination of a random basis, right? But the things that we don't have too much control on those random bases because of the hidden matrices, randomly initialized hidden matrices and biases. But here, we have this file effect, this coordinate embedding. We can explicitly control what it is. In this work, I just use random for features, but of course we can use other coordinate embeddings like Chebyshev polynomials or even finite elements. We have more control on that. And this technique is quite similar to that extreme learning machine stuff. These are the remarks. And here's a summary of this architecture. The key thing is that this ParaNet is initially a linear.
Sifan, I have a question. And actually, that's what I was wondering all the time. How about if you, and I don't know if in your experiments, if you did that, if you use the method of random projections as an initialization, as opposed to all these multiple layers and so on, because that's really, really fast. So does it make any difference?
Yeah.
Which one is better, the Pirates or the method of random projections for initialization?
You mean at initialization? Or you mean only at initialization or what?
Only as initialization.
Okay, so here there are something slightly different. So here for those random projection stuff, I guess it has some trouble when tackling nonlinear PDs, right? At least from my experience, it's very easy to get stuck at some local minimums.
Well, Steve Dong, my former postdoc, claims that he has solved that problem. So he has published papers on that.
You mean that we can directly solve a nonlinear least square problems?
Yeah, that's what he does. I mean, he has published several papers on Berger's equation, Euler, Alan Kant.
Yeah, I saw that, but I saw he tried to concatenate the features from hidden layers. And
he only has one hidden layer.
Yeah, but really? You mean the papers from Stephen Dong, right?
Yeah, the method of random projections have only one random layer. I think people are listening here, maybe pitching, but I think there's only one hidden layer. There's no.
That's correct, George. This is Mario.
No reason to have more.
And it should be only one layer with the non-linear least square for both of these MPDs.
Yeah.
At least from my
George, sorry to interrupt. George, actually, Steve Dong has I think he recently uploaded a paper that he did exactly what Sifan just described. He concatenated several hidden layers together to make a larger, wider layer. So there's one new paper about that.
Oh, I see.
Yeah. And basically, I tried that. Actually, I'm very interested in that approach. It's really easy to get, and it's very sensitive to the random seed, and it's very sensitive to the batch size, the collocation points, and of course architecture, the width of the neural networks, and also for the long time problems and my point is that it's very sensitive. It's very easy to break things up. That's my experience at least.
Okay, please proceed. Actually, I don't know if Kostas Sietos from Naples is listening.
Yeah.
Sign up. Can you inform us, Constance, about this?
Yeah. I mean, the random projections comes actually from the Johnson-Lindenstrauss theorem, right? So you can prove that with one hidden layer, you can train in both, let's say, elliptic PDs or semi-linear PDs, but also parabolic systems using one hidden layer, actually doing Newton or doing Newton on a Moore-Penrose pseudo-inverse. And actually you can compete. We have a couple of papers, George knows about that you can compete also in some cases where you have a sub-gradients, also establish numerical analysis methods like finite element methods. So, I mean, this is kind of surprising. There's some, I mean, random projection seems to be more efficient when there are sub-gradients or stiffness in the system, where, also a classical numerical analysis, I mean, they have hard time to converge. Yeah, I see the analogy. I want also to ask a question about this at the end, about how it compares to what Sifan shows. Yeah.
Thank you.
Thank you, George.
Sifan, please proceed with just some random thoughts of random projections.
Okay, thank you. But basically, it's a kind of a bonus. We can do that, or we cannot do that. It's a kind of a bonus. That's the thing. As a summary to this architecture, so basically this ParaNet is initially a linear combination of a chosen basis. Then it's a very shallow networks, right? Then we try to avoid all those issues, initialization issues of deep MLP derivatives. And then this ParaNet approximation capacity will be gradually recovered during training because those nonlinearities alpha are trainable. So during training, once these alphas becomes non-zeros, those residual blocks will play their roles. Okay, then I'll go to the results section. In this section, I want to answer the following questions. The first one is this physics-informed initialization helpful? Second is the adaptive skip connection helpful? Is a gating operation helpful? Because these three things are the key difference from a standard MLP. And the core questions will be, can this ParaNet facilitate efficient and stable training of deep PIM models? Lastly, can we achieve better results? So that's the questions we want to answer. Here, I want to introduce the baseline. From the architecture, we use the random feature embedding to mitigate spectral bias. We use modified MLPs of reasonable depth and width with different activation functions depending on their performance. And each dense layer is augmented by this random weight factorization. For the training, we use self-weighting scheme to balance losses. We use causal weighting to impose the causality, and we use time marching for tackling more challenging problems. For general setup, we use Adam as the optimizer. We use a linear warm-up and exponential decay. We train the model for enough long iterations to ensure the model is fully converged and with relatively large batch size. This is a baseline. I want to emphasize this is kind of relatively strong baseline we have. I saw lots of papers trying to compare their result against vanilla pins framework, which are supposed to be relatively weak baseline. So here, we believe such a can be set as a relatively strong baseline. Okay, so the first benchmark is again the Allen equation. First of all, I want to show some ablation studies. Starting from left, I show the resulting relative after errors of using different data sources to initialize the last layer. Here, IC just means we initialize the last layer to fit initial condition, and let's linearize PDs just means that we initialize the last layer to fit the solution to this linearized PD, which is a simple heat equation with very small diffusivity. Okay, you can see there are no differences. So in the rest of the benchmarks, I just simply use this to fit this initial conditions to do the initialization of the last layer. Let's move forward to the second application studies. That's about the effectiveness of the list initialization stuff. You can see for list physics informed initialization, it can benefit both architectures. We get smaller test error. But for both cases, this architecture, this ParaNet works better. Then let's move forward to the last figure shown on the right. You can see for deeper networks, this modified MLP doesn't scale. It's not very scalable. For deeper networks, its predictive accuracy increases. But in contrast, this ParaNet we can get consistent improvements by increasing the network depth. Okay, in this slide, I just show some realizations and the convergence of losses as well as a test error. Something interesting is about this nonlinearity, those alphas during training. You can see just after a rapid change in the early training process, it just kept almost as a constant in the later training. And another thing is that those alphas are not very large. It's about 0.01. In other words, for this benchmark, actually, the model thinks it may not need so much nonlinearity to capture the solution as well as their derivatives. On the right-hand side, I just give a table which summarizes lists a series of work on PIN's literature focusing on the same benchmark. You can see from the original formulation, it doesn't work. But after a series of works, we can gradually reduce the error. But this ParaNet can give us a state-of-the-art accuracy. Okay.
Sifan, one question here. It's related to the cost of the method. Because I assume that, for example, when you use the modified MLP and you have a lot of operations going there, right? Because you have like every time you jump one layer, you're going to have multiplication of the encoded inputs every time, right?
Yeah.
So that makes the problem a bit slow. And then if you add also this additional, well, I assume that the gating operation may not make it that slow because you just have this 1 minus alpha and just the addition. But the two gating operations may make it a bit slow, right? If you compare it with normal vanilla PIN.
Yeah, that's a great question. Yes, I agree with you. This gating operation slow down the training process, slow down the training time. For each iteration, it takes more time. Yeah, that's the case. But
yeah. So in that case, did you do some type of ablation study for the time too?
The key thing is this adaptive residual connection. I want to say that the computational cost for that is negligible. The computational cost of this gating operation is relatively large. But I want to say that if you remove this gating operation, this adaptive residual connection is still helpful, still works. And I'll show some application study on that.
And also, that was related to my first question. Like, I assume you're gonna show it later, but because you said about your ablation study. But ideally, only your gating operation, the skip connection operation, only the alphas should be enough to get back the connection to not have the vanishing gradient. So ideally, only that part should be good enough to.
Yeah, but from our experiments, we found that this gating operation can help model convergence and also improve the accuracy.
Yeah. Okay. Yeah. Thank you.
Okay, so I just move forward to the next benchmark. So here is a gray skull equation, which is a 2D reaction diffusion system. We consider such a hyperparameter setting. These are the results. On the right-hand side, I just show a simple animation or comparisons between the reference solution and the predictions. By eyes, I can't see any differences. But down below, I show the the evolution of errors, you see lots of spikes because I use the time windows. So every spike just represents we switch to another time window and retrain the model. But the key thing is that here we use different activation functions. But for 10H and the switch, you can see modified MLP is not stable at all. After the first time window, the error immediately goes to about around 1. So it doesn't. It just the predictions is just garbage. But for ParaNet, it's really robust against the choice of activation functions. Whatever activation functions are, it's quite stable. But of course, the switch activation function gave us the better accuracy. On the next slide, I want to show some application study of this residual block. The first thing is about the initialization of this alpha. You can see if we initialize alpha by 1, then immediately all the magics disappear. We get increased errors for when training deeper networks. This only works when alpha is equal to 0. It is initialized as 0. On the right-hand side, I show some application studies on the gating operation. You can see that this gating operation is really helpful in improving the accuracy, but not too much. But if we pursue the state-of-the-art accuracy, sometimes I found that this thing can be helpful. But if we remove that, we still get reasonable accuracy, decent results. Okay, I just want to use this application study to show the effectiveness of the this gating operation. Does this answer your question?
No, actually, this actually is what I was saying is like the gating operation looks like it's like one of the main contributors. Sorry, not the gating operation. How you call the blue line again? Okay. You have 2 gating operations, and then you have, how do you call the equation in blue?
Yeah. So this alpha is more fundamental. They make
Yes.
fundamental difference.
Yeah, but my question is, did you try without the yellow lines?
Yeah,
because
this blue column without the gating, I just simply remove the yellow ones.
Oh, okay.
If you simply remove the yellow ones, you can still get some errors below. It's about 1e minus 4. It's about 8e minus 5.
Yeah, I see. But it looks like it seems the yellow lines are the expensive ones. If you just stick with the small ones, then you can train faster, right?
Yeah, exactly. If you care about the training time, definitely you can remove those yellow lines, but you can get similar or less accurate results with less adaptive residual connection.
Understood. Thank you so much, Sifan.
Okay, let's move forward to the last benchmark. This is a lead-driven captive flow. We have this Navier-Stokes equation, incompressible Navier-Stokes equation in the velocity pressure formulation. And we have this problem set up. This is a standard benchmark in CFD. We have a moving top lead with velocity u, and we have 3 walls characterized by the non-slip boundary conditions. To avoid top singularities on the top 2 corners, we use this soft boundary conditions on the top lead. And for this benchmark, we consider relatively large Reynolds number, 3 to hundreds. And for C0, we choose 50. And in this slide, I just show some results. The first row just shows the predictions and the comparisons between predictions and this well-known reference solution. You can see we get a good agreement with each other. Down below, this is application study only on the model depth. You can see even up to 24 layers, we can get stable training, and we can consistently improve the accuracy. I agree that the improvements are not so large, but I believe such a consistency is quite important in the scalability.
Sifan, another question.
Yeah.
For this case, when you do the first initialization, when you initialize with these least square errors, here you only have velocities for U and for B. How do you deal with P? Because you don't have information of P, right?
Yes, that's a good question. So we don't initialize P. We only leverage the information we have.
So for P, for the last layer, you just do normal chloride.
Yeah, we just use a normal initialization for the weight vectors corresponding to P variable.
Got it. Thank you.
Okay, so this is the application study, and let's really conclude my presentation. As a brief there's still some additional results I want to highlight. Actually, there are a few more benchmarks in the paper, but I didn't introduce in this presentation. The first one is this KdV equation, which is third order PDE. Second one is this Ginsburg-Landau equation. This is a complex two-dimensional reaction diffusion equation. But for all the benchmarks, this PirateNet can give us better accuracy. Yeah, so that's really concludes my presentation. So as a summary, we start from the hypothesis that convergence in pins training loss implies convergence in derivative networks. Then we show some propositions for higher order estimates in the setting of second order linear PDEs. Next, we review that the initialization pathologies of MLP derivatives, and this causes problematic training of PD residual networks. Then finally, to solve this issue, we propose the so-called PirateNet to facilitate stable and efficient training of deep pin models. So that's a summary. In terms of the future work, there are two things I think worth exploring. The first one is that more suitable coordinates embeddings. Here in this work, I just use random for features, right? But for different problems, I believe the suitable basis should be different. For example, for non-periodic boundary conditions, maybe Chebyshev polynomials is better. For solutions exhibiting fine features, maybe we need some radial basis stuff. The second direction is about extending PirateNets to the physics-informed neural operators, as I believe that similar issues will happen for when you're adding the physics laws for the neural operators, as long as you use AD to compute the derivatives. So some principles in this PirateNet, I believe they can be used in less more general cases. Yeah, that's all about my presentation. Thank you for listening, and I'm happy to take any questions.
Thank you so much, Sifan, for your great talk. Somebody put something. Yeah, Mario put the deep neural network with random projection paper in the chat. So we open the floor for question. Do we have any question? Yeah, go for it.
I have a question, Sifan, about your hypothesis, which is right for pins, but it's not right for G-pins. So, for example, if you look at our G-pin paper, we show convergence of the derivatives, in fact. That's the thing. So, of course,
Yeah,
the cost of G-pins is higher, but I was wondering what is, especially with G-pin implementation that Zheyuan, the previous speaker, has actually at Singapore. It's very fast. It's and also using sampling instead of derivatives. But are you claiming that G-pin will have the same problem?
What problem? You mean the?
Well, your hypothesis is that the derivatives do not converge as you go deeper.
No, the hypothesis. You mean this hypothesis or other things? This is the hypothesis.
Right.
And then you mean this thing, this trainability of derivatives determine.
Yeah, exactly, yeah. So I claim that in G-pins we don't have that problem because we look at. I mean, I haven't tried the depths of 10 and 20, but we see, for example, convergence of derivatives, and that's what you're monitoring, because you see when you take the gradient of the residual, right?
Mm-hmm.
It's like you're forcing the previous, just like you said with the question that one asked you, in the Navier-Stokes, you have the gradient of P.
Yeah.
It's the first derivative, it's not the second derivative. But you are imposing residuals which are into the second derivative. So the first derivative really doesn't matter. So you were one derivative ahead, so to speak. So the same thing with GPIN, you have the derivatives of.
No, I guess
second.
the things that here, I never say that the network derivatives cannot converge. What I say is that if some issues happens in the trainability of network derivatives, then eventually we get some issues in minimizing PD residuals.
Okay, so let me rephrase the question instead of making that. Do you think that using a Sobolev norm in the loss function will change this?
I think this is not really related to. Of course, I believe that higher order derivatives it's harder to train, but that of course this is kind of a trade-off, right? You have a higher order derivatives, you try to impose higher regularities to your model. That's kind of the benefits. But on the other hand, you may have a harder training optimization process. It's hard to
okay, so
quantify.
so actually you're saying that it's the opposite, right? You're saying that GPINs or Sobolev norms will suffer even more as we go deeper.
Maybe but I don't do any experiments about that. It's interesting to test that.
No, you just told me that. You just told me that. You just said that that higher derivatives will suffer more in training.
Yes, at least from all those things, I believe I can give such a claim. Maybe I'm wrong. I mean, maybe I'm wrong.
Yeah, I don't think so because if you look at our convergence plots, for example, we converge in much fewer iterations and much fewer with GPIN and also, but we have to look at pathologies, like you said. So
yeah, again, I
something
mean,
to consider.
this GPIN is helpful in improving the model accuracy, right? But on the other hand, if you don't have suffer from the optimization issue, it's kind of you have harder training process, but you have a better loss function. It's kind of a trade-off. It's hard to quantify which one really determines the final results.
Yeah.
But I want to say that for GPIN, we only consider less loss functions. Things may become different for JPINs. For JPINs, we get higher we take derivatives with respect to less PD residuals, right?
Yeah. Yes.
Then ideally we may expect higher regularities in less inequality.
It's kind of training the Sobolev norm. Yeah.
Yeah. But I want to another remark I want to give is that for hyperbolic PDs, sometimes this hyperbolic normal GPINs is important because they will get if we in the series side we cannot prove similar inequality given the current form of the losses. We need higher regularities for the initial condition to get the same inequality.
No, for hyperbolic you need to use total variations. So different norms.
Yes.
Handy and I have some results on that. But you use total variation, not these norms.
Thank you. Do we have any other questions?
Yeah, may I? This is Kostas Ketos from
Yes.
University of Naples. Thank you. Thank you for your talk. Okay. Yeah, I would like to ask about your board in the bendings. You use also random Fourier feature, but this, I mean, this choice should be consistent with your boundary conditions. Otherwise, I mean, you already impose some bias there. So if you use random Fourier, then you assume periodic boundary conditions, and when you don't have such thing, I mean, you take a solution that has an error in the boundary, so it's not the correct, let's say, operator.
So here, let's.
I mean, I'm saying this because also what you've presented, your loss function was relatively also big. Yes.
Thank you for this question, but here B is sampled from a random basis. They are not from a fixed frequencies. So it's not necessarily exact, it's not really exactly encode the certain periodic boundary conditions. Of course, there is such a tendency, but
yeah, but if you use cosine sine, then you have also, if you have, I'm talking about not, you know, fronts or for hyperbolic more things that you have a steep gradients, then you will have the Gibbs phenomenon there. And then, I mean, cosine sine are not good.
yeah, that's why, yeah, I totally agree with this. That's why I think different bases, we need different bases for different problems, and we may get better convergence.
Right.
And this is kind of just standard choices for in general, this thing is helpful. So I just use it in this work. Of course, you can remove that. Yeah, just to get
yeah, you can use, I mean, other bases for doing random projections, right?
yeah,
the
any
kernel or kernel function or even the sigmoid have better properties at the boundaries. This is what I'm saying.
Yeah, thank you.
Thank you so much. So do we have any other questions for the speaker? So I think we don't have any more questions. Thank you, Dr. Wang, for your great talk, and thank you, Hu, for his talk. Thank you, everybody, for joining us today. It's time to close the session. Have a great weekend. Bye.
Yeah, thank you. Bye.